All right, so the first thing that you guys know is that lecture is Friday from 10 to 12. What I want to say is that I'm going to do, so let's say lecture, this is the majority of the course. It's going to be, I will also be assigning like problem sets and stuff, but we'll get to that in a second. One thing is that this is, I guess it's 11:50. See, this is like an hour, 50 minutes long, which is kind of long, I think, for a lecture. Hey, Simon? So I'm not going to be probably using up the full time of that for like a lecture like yapping at you. Instead, what I'm going to do is I'm going to do, let's say, if you guys are used to, say, hour and 15-minute lectures, roughly. So let's say that that's going to be like an hour 15 is going to be the sort of standard, like how a lecture would normally be in whatever course you're taking. That's like two a week and then a section. Of course, we don't have sections, so let's say 1:15 is lecture time. And then the remaining time, we still have the room, so we don't have to evacuate. But I want it to be like, so we have like roughly 35 minutes. You know, this is flexible, but we'll have roughly 35 minutes for sort of an open discussion time. And this is going to be, for example, if you have a question that was really long-winded, like maybe would have interrupted the flow, so I'll say maybe you can defer that to then. Or if you just have questions in general, or if we can discuss, like I will be assigning PSETs that you can maybe do, we can discuss that, just anything. And my reasoning for this is that, like, for any, let's say for any interesting course, I always feel like there's, and maybe it's me, but there's always like a couple people that say after go to class to like talk with the person that was lecturing, and then it's like sometimes you have to leave and they have to go to office hours, but I figure those are sometimes some of the most valuable discussions to have, and I'd like to open that up to everybody. And this is like kind of the perfect place to do it. I really encourage, I'll write it down, I encourage coming up to the board during this time. Like, you don't have to, if it's just a question, but if you have something that would be expressed the best that way, I think that's also like good practice, so I really want to encourage that. So this is going to be the bulk of the course. Let's see, I don't think I have anything else to say about the lectures. The next thing that I want to say is, how are we going to do like grading in this class? So you can see I'm just passing the sign-in sheet around, I don't know, just get to it by the end of the day, or at the end of the thing. That's going to be, again, this is on the syllabus, but it's going to be out of 200 points. So you can have more than 200 points, but like 200 points is kind of the maximum that matters. So 90 of those will come from attendance. And that's so like 10 per lecture. I don't think I'm going to do a lecture pre-finals week because I will be busy and you will probably also be busy. So we'll just do 9. And then let's see, at least 110 from PSETs, but there will definitely be more available. So you don't have to do like all of them, and I will probably grade pretty lightly. It's going to be like completion, let's say like roughly completion. You can't just write like, I don't know, a copy pasta, but that's fine. So you'll notice, and the way it'll work is 100 points is equal to 1 unit, and 200 points equals 2 units. So you'll see, if you want to pass the class, you technically do have to do some of this. I will say 5 of these points from the PSET will come from like, one of the things that I'll send after this lecture today is going to be like, what do you want to see in this course? Like, what are you interested in? That type of question. So it's just like write a couple sentences. And then at the end, I'll also have a question that's like, reflect on the course. Like, what did you think about it? Just feedback. And those will be worth 5 points each. So if you just want to pass, you just have to do like 6 sentences of work. But I do want you to at least engage to that extent if you want to pass the class. If you don't do that, I really don't want to fail people, because that would be really sad for a seminar, and I probably won't, but please just do that, because I would definitely like to, I was just expecting that you're going to fail, by the way, Gavin. So just, yeah, that's all I ask, like just give me some very slight feedback. I think the only other thing, and then if people have questions, I'll pause after this. The only other thing is, let me say references. So references for the course are primary lecture notes. So like I've typed up, I mean I need to finish typing up for the whole class, but at least for more than the first half, I've typed up lecture notes that you can follow for the entirety of this class, and they will pretty much be one-to-one with the lectures, and we'll get to it in a second, will be with the exception of the first one. So that's the primary reference, but the two things that I use is for like the first half of the course while writing this is a book called The Quantum Theory of Motion. Motion. And this is a book that is pretty much like the comprehensive resource on Bohmian mechanics. If you know what that is, I don't know. Has anybody heard of that? It's called pilot wave theory. I mean, I'm not actually going to be doing it, by the way. It's like arguably an alternative. I mean, it is an alternative to like the Copenhagen interpretation of quantum mechanics or single particle quantum mechanics. It kind of breaks down in a lot of cases. But the sort of the baseline theory is very rigorous, and it's only sort of the interpretation and things that they talk about that is iffier. But one thing that it has that's really useful, this quantum theory of motion, or I'll say Bohmian mechanics, is that personally I feel like it's a lot more physically intuitive to understand it, because again we'll get to this, but it's like it kind of describes quantum mechanics in a way that's very, very analogous to like classical fluid mechanics, which you can maybe have a better intuition for like things flowing around and swirling and stuff. So that's the first half of the course. This is the primary resource. The second thing is, because we're going to be moving on to the quantum Hall effect, I really do quite like David Tong. Let's see, this is QHE. Google will know what you mean if you type that in notes. Primarily just the first two sets of notes. If you go to his website, it's very like nicely formatted. That's the second reference sort of for the second half of this course. Very, very good pedagogical resource. I think that, I mean, you could probably learn a lot just by reading those. And both of these expand upon everything that we're going to talk in this class quite a bit. So I would reference those two primarily if you have questions more.
Who wrote Quantum Theory of Motion? Do you?
I have it.
It would just be searching that would be good enough.
I think I posted, or I'm gonna post like a link to like
okay.
to a place to buy it, but I don't know, what is it? It's like 1993. Peter Holland. I don't know. Do you know him?
Holland?
Yeah.
No.
Okay. Yeah. He's. I don't know. It's definitely not an introductory quantum mechanics text because it's pretty complicated. I mean, it does Hamilton-Jacobi theory at the beginning, but we won't be doing that. We're gonna. But it's a good book. I think that after you kind of know quantum mechanics from like the 115 series, it's actually a very, very interesting reference, and it has some really, really cool explanations that maybe are iffy, but are at least very different than the ones you'll see pretty much anywhere else. Okay, and then the rest of them would be selected like papers / lecture notes, which sort of when I get to like the topic that I use those for, I will just like post a PDF or I'll post a link to them on Canvas. Okay, I think that's all of the logistics. I think so. So let me pause. Does anybody have any questions right now at all? Yeah.
What if we get like 170?
Well, I mean, okay, like it's units. I mean, I don't know if you actually care about units. If you really care to get 2 units, then you should do the 200. It probably won't be more than like 4 hours of work total. Like I would say there's probably going to be, if you did every homework problem perfectly, you could probably get like 600 or something. Like I'm going to be doing, you know, I'm going to be very generous with that. So don't worry about it. If you need the 2 units and you don't do that, like, I mean, I don't know, you could come talk to me, but it shouldn't be too hard. Like this is a pretty, also it's units. It's not like grading. Like this is pass, no pass. Sure. So I don't know if you need the units, then maybe, but I would prefer that to be fairly strict. And yeah, I'll say I don't want this to be, I said this in the syllabus, I don't want this to be like any amount of a time constraint more than like the lectures really. So if this is like hindering you, I mean, you can talk to me, but I really am trying not to make it like be a big time commitment. So I'll say please don't try not to worry about that. I don't think it will be an issue. Anything else?
Maybe it's just me, I'm having trouble reading the board.
had a
Maybe I
wording.
should sit on the other side, it's kind of a glare.
Let me,
Here's another piece of chalk I brought.
I have, oh, is this,
Well, I don't know
is this the
if it's better.
KITP chalk?
I don't know, I mean,
It might be
next time
better.
I can bring some.
I don't know, let's see, can I write, if I write like 1, 2, 3, 4, is this better?
That's better for me, I don't know.
Okay, maybe I can just, yeah, it is writing better. I brought color chalk, I don't know. We'll see which colors are visible on the green.
Yeah, maybe just use this one, I mean, I'm gonna.
Okay, if you're,
box there.
thank you.
Yeah,
That's very,
soft it on.
okay. I'll take this one for now.
You can just take the box.
Okay. All right, well, is that clear to everyone? Can people see? Okay, cool. Yeah, no, I know this, I'm not used to writing on green, so if you have issues seeing, especially the colored ones, please say so. I know that's an issue I've had with Dr. B's lectures in these rooms before, because they're too hard to see. Okay, let me now move on to like the sort of central, let's say, thesis of the course. I can do it here. So this is kind of what I say in the overview of the syllabus. Or maybe let me expand this. So as I said previously, all of the lecture notes will pretty much be one-to-one with the lectures, with the exception of questions and stuff, except for this first one. If you go in, I believe I posted it. I don't know if anybody has a Canvas pulled up right now, but I've never done this before, so can you see the first modules on Canvas? Like it says lecture 1 there?
Yeah.
Okay, cool. You look at that, that's a much more mathematically like heavy lectures, set of lecture notes. I mean, it's not that dense, but it's a lot more dense than I think that I want to do for this first lecture. So I kind of realized that around a week ago. But I do want to, I'm posting it as a reference. It won't really be at all related to what we're going to talk about today, like directly, although I think it does serve as a cool preface to the course. So today, like I said, I'm just going to be doing like an overview of what we're going to be talking about. And yeah, that will be that. If you want, I could maybe post a summary. I mean, it would take me not that long to type up. So if you want, I can post that as well. Okay, but today, let me go over, let's say, overview. Oh, this is a lot nicer to write with. And let me sort of talk about first the sort of central thesis of this course. So let me divide this into something like this maybe. So it's section off the board.
That's on the
Wait,
screen.
that's
It's
on
off
the
the
screen.
Okay, good. Is this? Can you?
Yeah, that's on the screen.
Okay, cool. Do this. Okay, good. So overall, this course is a response to the PHYS 115 series, in which let's say 115A, I guess let's say is really the one that, because I'm assuming that is a prereq. 115A, you learn about the Schrodinger equation and the quantum wave function psi of x and t. Towards the end, you do start talking about like Dirac notation and talking about how that's really like a projection onto position space, that sort of thing. I think that you should have all covered that in 115A, but really it's mostly focused on, you have a Schrodinger equation, you add like a potential to that, and then you say, I'm gonna solve for the wave function that is the set of eigenfunctions. And that's cool, and whenever you do that, if you ever actually like, beyond anything that you do beyond that is always to deal with the quantity, which is the norm of the wave function squared. This is the probability density. Let me call it rho. This is the probability. Is this writing big enough for people to see? Okay. That is the probability density, and that's pretty much all you care about in that course, and pretty much for the entire 115 series, mostly. it is the thing that we care about because it's the thing that's observable, right? Like this thing, as you know, I mean, it's not exactly a probability, you have to like integrate it, but it's basically, it's a probability of finding, you know, if you measure something, you'll see that'll give you the probability of finding it somewhere, roughly. And that's what you care about because that's what you can see in quantum mechanics. It's like, that's how you would do any sort of measurement. But it's not all of the information that is contained in the quantum state, right? Which, you know, the quantum state is contained in the waves, like the ket side, in position space, right? This actually contains all of the information about a definite quantum state. And this does not contain all of that information. Why? Because psi of x and t, you could write this as the magnitude, or I'm gonna write the magnitude as the square root of rho. So I'll write, this is the square root of the density, rho x and t, because it has the square, times a phase, which is e to the I theta of x and t. And the notation I've chosen to use here is, sometimes people would write this like as like theta over h bar or s over h bar. I'm gonna work not in units of h bar equals 1, but for clutter's sake, I'm gonna absorb the h bar into this. So the point is that you have this information, and now let's see if this works. So in the 115 series, I think that's visible. In 115, you only really care about this, or the square of it, but it's the same thing. And we're gonna be focusing on this in this course. Because there is information contained in that, and it's very, very important information. Okay, now you might be thinking, or you might have a small objection to this, and that is that you do actually care, there's at least one section I know where you talk about phase in quantum mechanics, because you talk about, suppose you have a wave function that's like psi is equal to, let's see, okay, let's say, but wait. What about psi is equal to, say, like some psi, psi1 plus e to the I times, I don't know, something alpha times psi2. Right, this is the relative phase discussion. I think that you all talked about this in 150A. It's like, you know, this is like a point that they make that like, you can multiply, or we'll get to that. A global phase doesn't matter, but a relative phase does matter. And that is like a thing you talk about. But the problem is, or not the problem, but the thing is that this discussion is still talking about this, because why does this matter? It's because when you take the norm squared of this, you get what? Psi1 squared plus psi2 squared plus, okay, wait, what is this? It's 2 cos, I think? Yeah, 2 cos alpha times norm psi. Let's assume these are real. Let's just say. Let's say those are real, so that I don't have to worry about that. Right? And then this thing is how you know, this is like an effect of the relative phase. Like that is an effect of the relative phase, but it's not like, it's just something that actually still has to do with the probability density, right? Like we inserted we basically explicitly showed that there was this thing, and then we showed its effect on the probability density. But what I'm talking about is, no, I want to write this in polar form and then consider the overall phase of it. So this is, but I will say, the thing is that like, or let's say, so this is sort of the discussion. This is still important because the thing is that it is still true that the actual probability density, the thing that you can measure is like the probability density. So if you ever want to measure the effects of phase, you have to do this thing where you create a relative phase and then that manifests in the probability density. So it is true that this is extremely important because this is how you actually like tie everything we're going to talk about in this course to a reality, to an experiment. Otherwise, it would just be some philosophical, like logical thing that like has to exist mathematically, but there'd be no way to probe it, which is like, then you can argue like, is it even real in the first place? So this thing is utterly important. Let's see. But it isn't exactly what we're talking about in this course. Okay. So then you might ask, let me see for a second. And let's say, so okay, that's what I've said. maybe this is being redundant, but let me then say another objection is, but let's say e to the I, the norm of e to the I theta of x and t times a wave function is just equal to the norm of that wave function because it's a unit vector, or I mean it's a unit complex number. So why does the phase matter? Right? It's like, if it doesn't, you know, maybe in this weird way with this relative phase, this is how you would observe an effect, but like, why does it matter at all? Because it itself is an overall phase, and so it doesn't, maybe we'll put the square here, it doesn't, like, you can't measure that, right? That's, you have to be very clever to do it, and it's like, well, what's the point of it? Well, it certainly does matter because it is, like, it is information about the quantum state, and the quantum state contains that information, so it probably has to do something, but, you know, I think that it's really hard to see how it's important. Like, what is the role of it? At least even in just like a philosophical or like a mathematical sense. So that is going to be the focus of the second lecture of this course.
That's your question? Is it okay?
Hmm?
Yeah, what if you measure the momentum? I mean, here you're talking about
Yeah,
measuring
so we'll get
about that.
yeah. So yeah, let me maybe do that right now. Do I want to? Maybe let me. There's like a section that I'm gonna talk about that, and we will talk about that. But yeah, so he's bringing up a good point, right? Which is that if you have momentum, it acts like a derivative. And well, I'll write this down, but I'll just say it now. It acts like a derivative on this, and so like if you measure that, it's gonna do like product rule, and so you're gonna have some change in it, and that's a really important topic in this course. And I'll sort of expound upon exactly how important that is later. But that is, for example, one reason why you might say it does contain information. It's because of the momentum. And also the time dependence is the energy, because that acts as a timer. So, but I want to draw a picture that sort of encompasses all of those things. And that is where this sort of Bohemian mechanics view comes into play. That's where this starts mattering. So that's going to be the focus of lecture 2. So yeah, I'll be like Dr. B, I'll put the thing there. So these numberings, let's say this one is roughly 1, although 1 is like all of this. These sections are sort of going to be subdividing each of the lectures, and I'll just be going over what topic we're going to cover. So the lecture 2 is going to be focused on explaining and making intuitive and physically meaningful, or giving physical motivation for what the phase tells you. So, okay, what we're going to do is we're going to move from the Schrodinger equation, which I will denote as SE, to this thing called, or the set of equations called the Madelung equations. Okay, I think I can use the pink. The pink shows up pretty nicely, right? Okay, I think it shows up bad on the camera, but if you guys can see it, that's what's important. So the Schrodinger equation, this is sort of has the emphasis, like fundamental quantity is the wave function. Okay, so in the wave, that's not how you spell wave. The wave function, as I said, contains all of the information about a quantum state, so it is correct. This is an equivalent, with a caveat, formalism, that it, at least for the sort of standard 115A quantum mechanics that you do, where it's like p squared over 2m plus v of x, equivalent formulation where it splits it into two things. We talk about the probability density, rho of x and t, or really the square root, but it's whatever. And also then we get a coupled equation, so we have one equation that sort of, no, let me not write that. You have an equation that couples the probability density and the phase field, theta of x and t, which is defined sort of over here. So you get a set of coupled, and they are also nonlinear PDEs for the phase field, or for the probability density and the phase field. And like I said before, this is going to sort of give a fluid mechanics interpretation And what it will say is that the sort of, if you sort of couple rho, let's say rho in this context represents the probability density, but I'm gonna put in another word, fluid density, where now we're sort of doing this fluid density. So you can imagine, like, I mean, you've probably imagined before, like sort of the bumpy hills of the wave function. Think about that as representing the density of a fluid at every point. That's kind of like how dense is a fluid. But the thing is that if you have a fluid, you can't just specify its density, right? Its density just says, okay, that's what it is right now. But the thing that actually is interesting about a fluid is that it's also moving. So at every point in the fluid, you also have a velocity field that tells you how much the phase is, how much that fluid is moving. And what we'll see is that the spatial gradient, or we'll work in just one dimension for this lecture, but I mean, it generalizes very easily. The gradient of the phase gives you, there's like a, let me say, h bar over m times the gradient of the phase gives you the fluid velocity field. So rho tells you how much like the density of the fluid, and the phase tells you how is it moving. It tells you how that probability fluid is going to flow. The distinct difference between this and classical mechanics is that, unlike in classical mechanics, you can't observe this. So it's really weird, but it exists, and it's telling the probability fluid how to flow. And we'll make all of this more precise there, but this is the idea. So now you see very clearly what the point of the phase is. I'll say, like, you see very clearly what the point of the phase is because it's the other half of the puzzle. You have the density, which is what we measure at any given point in time. You like collapse it, say. But then, you know, if you want to consider time evolution or, you know, how it's flowing, the velocity is really important, and that's encoded in the phase. We'll also find that this one is maybe going to be a little harder to imagine, but like, right, we considered the gradient of the phase. There's also a time dependence, so the time derivative of this is actually going to give you the sort of energy field, and this is a little bit harder to, yeah, this is like the energy field of the fluid as well. So now we sort of encapsulate everything about the phase, where we have both its time dependence and its spatial dependence give you the other things that you care about this probability fluid. And I'll write down one of the equations that we'll get is, like I said, you have these sort of nonlinear set of two coupled PDEs. One of those is something that you're actually very familiar with. One of those is going to be the probability density, or the probability continuity equation. So partial rho partial t plus divergence, or since you went through today, we'll just do this, partial respect to x of j of x and t equals 0. We're now, I think, have you all seen this before? Right, you do this one with 15a. We will derive this, but there's also a missing extra equation that you need, which this is the one that just says continuity is conserved. And then the point of this is we're going to derive the second equation, and at the same time we'll derive this, that will sort of fully describe the quantum fluid in a way that is almost entirely equivalent to the Schrodinger equation. So that's the idea. So this is the point. We've now, after this lecture, we will have developed an intuition for the fields. Let me maybe write down explicitly the quantities that we care about. So I said this. I'll write down the actual like quantities that we're going to write. So that will be v of x and t, which is the probability density, or the velocity field, is going to be h bar over m times the gradient of theta. We already have rho. And then this thing that I'm going to call the energy field, eta of x and t, which should be a vector, is going to be equal to minus h bar partial theta partial t. Okay, so just as a reference, this is what we're going to care about. So then in the Madelung picture, we really have three quantities that we actually care about, two of which are given by theta. We have rho, v, and e. And e will come into this equation. Okay, so now, let's see, we're at 10:34. Maybe I should speed up. Yeah, no, I'll pause after this one. Okay, so now that we've developed this theory, and there will also be a discussion of Galilean invariance in this that I'm not talking about, I'm going to now try to expand upon it. We're going to say, okay, now we have this intuition, and we're going to start talking about this thing called local phase symmetry. So once we have this understanding, we have our discussions, we can, we're going to start thinking about symmetry. So the symmetry, one symmetry that you know that you have, even in this picture, in the original Schrodinger equation, is that you know that, like we said, let me call this a global phase symmetry, is that, you know, e to the I alpha times psi, where alpha is a constant right now, is equal to psi, and also doesn't change the Schrodinger equation / Madelung. It's the same thing, so it doesn't actually change the probability density, and it doesn't change the equation of motion, so it doesn't affect anything. That's called a global phase symmetry, because this thing is a constant, and constant in this sense means global as opposed to dependent on space and time. This is a symmetry which is important, and it actually implies the continuity equation, but it's one that's built into the theory, and it's one that is intuitive. This is something that you talk about 115a. However, like we said, we actually care about this sort of phase field in this course. So let's see, we can see that this is obvious, but we want to see if we have local phase symmetry. Which is to say, let me put question mark here. This is to say, like, do we have the ability to say, is e to the I alpha of x and t psi equal to norm psi? So let me just ask quickly. Is that right? Is that a correct statement? Anybody? Do you think? Yes. Yes. So it is. This passes this question, but and I won't explain it in this language. I'll explain it in the Schrodinger equation that you're familiar with, like Matthew said. P hat, which is, remember, you have p hat squared in your Schrodinger equation, is kind of like minus I h bar partial with respect to x. So p hat acting on e to the I, okay, I'm being sloppy with like the operator notation, but you do this already. So e to the I alpha of x and t psi is not equal to just e to the I alpha of x and t p hat psi. Right, so the point is that you do product rule, and this is gonna like make that not the same. And because p is in the Schrodinger equation, this changes the equation of motion. Okay. So that's, I mean, it's not a problem, but the answer is actually no. You don't have local phase symmetry in your system. What we're going to do is we're going to say, but I want to have local phase symmetry. I really want that. I honestly tried to come up with like a good physical motivation. The truth is that you are just actually going to change your theory when you do this. But we're going to say, okay, but I want it really bad. So we're going to say impose. I'll call it LPS. So we're going to say, but you know, we don't have this symmetry in our system, but we're going to like impose it. We're going to say, I want this symmetry. And what we're really doing is we're forcing a redundancy in our description of it. And what we'll find in this lecture, this is going to be the main focus of this lecture, is that imposing this actually leads you, like it forces the introduction of the fields of gauge fields. Let's call this, I'll call it phi comma a, And in fact, just from this and pretty much just from this and everything that we've done before, you can find that by imposing local phase symmetry, you get out the laws of electromagnetism. Okay, let's say with a caveat. There's one thing that we have to do. We'll get to it when we get to it, but the issue is, the one thing that'll be an issue is that electromagnetism is a Lorentz invariant thing, and we're not talking about Lorentz invariance here, but we will discuss that when we get it. Pretty much like everything else, except for two of the Maxwell equations. You can get the electric field, the magnetic field, the Lorentz force law, and two of the Maxwell equations just by imposing local phase symmetry, and it forces that. So this is to me one of the most beautiful results, things that you do in physics. It's like, we have the Schrodinger equation, and just by changing our theory, which means that you want to make this a symmetry. So we want to say, maybe I didn't make it precise. We want to make it so that this is already true, but we want to make it so that it doesn't change the momentum. What we're going to have to do is we're going to have to modify the momentum to do that. And by just doing that, you get electromagnetism out. And this is yeah, so that's the focus of the third lecture. Let me see, how much time do we have? Okay, it's 10:40. Maybe we will end up using up all the time. Does anybody have any questions at this point? Is that clear? Yeah.
Why do we care so much about imposing this?
Well, like you're saying, well, we care about it because we get this out, honestly. That's like the big thing. It's like, let's say maybe I can motivate it this way. If you want to couple electromagnetism to a theory of quantum mechanics, the way that you do that is by imposing local phase symmetry. You have to change your theory slightly, and by just changing it, but we're going to do it the other way. We're going to say, let me just suppose that it changes theory slightly, and then we're going to get out electromagnetism. So, I mean, you could come at it from both ways, but I mean, it is the truth that electromagnetism exists, right? We know that it exists experimentally, at least. So this is how we can couple it. And the reason why this will be, I think, again, more physically motivated by considering this sort of fluid system, because we'll sort of imagine that what we have to do, because like I said, we have to modify momentum, is basically we have to modify our velocity field and our energy field in a way that like it's kind of saying this is what we have to do, and then when we do that, it's kind of like saying that you somehow change something about the fluid, but it's like unobservable. And we'll get into it, but I think that's mostly it. Yeah.
People have noticed that the imposition of local phase symmetry results in something that we know to be the truth. Why do you phrase the imposition of local phase symmetry as a change of theory rather than just the theory? Because
the theory that you have from 115A is what I'm referring to.
Oh.
This theory does not have local phase symmetry. I'm saying if we change from the theory that you're familiar with in 115A to a theory that has local phase symmetry, you get out these equations. That's what I'm saying. Sure. Kareem?
Yeah, I was just curious. I might have missed it or not understood in the moment, but how do we motivate our definitions for the velocity and energy fields?
We'll get to that.
Yeah.
So, I don't know, you saw let me maybe do this, and let's see, yellow is probably good. Let me say, just sort of sidebar, J of x and t, this is something that you can accept. You can write J of x and t as just rho v. Let's say equals rho v. Okay, so I mean, that's what this is really partial with effect x of rho v. So it's like what we'll do is we'll derive these equations, and then we'll identify the quantities that look like that. Because if you define these quantities this way, it looks almost identical to like a set of fluid equations. Also, I know that you guys don't do much fluid mechanics, so probably at the beginning of this, we'll like overview the main things we care about in fluid mechanics. And at least this one should make sense because it's continuity. The next one is a little bit less familiar, isn't it?
How do we define like quantum fluid dynamics? Like, is it something that we cannot measure classically, but we can measure in the quantum regime, or what?
Other way around. You can measure it, like if it was a classical fluid, you could measure specifically the velocity field of a quantum fluid. You can't measure.
Okay.
That's what makes it weird. But in a classical fluid, you could, of course, I mean, you look at it and you see how is it flowing.
But for quantum, hydrodynamics, you cannot measure the velocity field.
Yeah, not directly. If you want to measure it, you basically always have to do this type of thing, which means you do an interference experiment.
Oh.
So like this is still important. Like this is very key because this is how you actually measure anything. But you can't directly measure it. You have to like do this like convoluted setup where you, yeah. Anything else? Okay, cool. All right, I'll do it here. So that's the first, it's the first section of the course. I'll erase this a second. It's like all on Canvas. The first half of the course, or the first section of the course, is sort of focused on building this up. The next section of the course is going to be sort of talking about the implications of it. The implications of, we built up to coupling electromagnetism to quantum mechanics. Importantly, this is not quantum electrodynamics. Quantum electrodynamics means you make the fields quantum. We're not doing that. We have classical fields and then quantum wave function. But we have a classical theory of electromagnetism coupled to a quantum theory of like wave function dynamics, let's say. We might ask the question, we have, let's say, classical E&M coupled to QM. Are there any, let's see, quantum, let's say, non-trivial effects? So it's like, you know, like we have E&M, but is there anything just using this classical E&M? When you couple it to quantum mechanics, do you have anything that happens that is more than just the classical electromagnetic theory? And the answer is yes, and it literally all, again, has to do with its effect on the phase. Because like I said, the thing that we have to modify is going to be these two. We're going to have to basically add these guys to these. And so all of the modification is going to have to deal with like effects on the phase of like the wave function or the phase field, as we'll describe it in this hydrodynamic picture. So there's two non-trivial effects that we will discuss in this lecture. I guess we'll first, let's say as a preliminary, we'll discuss interference, which is the thing that I discussed already twice now about how this is important. So we're gonna kind of flesh out exactly how this works in the hydrodynamic picture and how it's like, you know, how we could actually measure these quantum non-trivial effects. So that will be a preliminary, and then we'll discuss firstly an effect that if you've taken 115B, you know, maybe you don't know very well, but you've heard of, which is the Aharonov-Bohm effect. And I'll just say it now. I don't think, so I know at least a couple people in here haven't taken 115B, right? So I won't maybe get into this, but I will get into the next one. This is a very, very weird, like, definitely the thing that I struggled with the most writing this course is this thing. It's a really, really, really weird thing that basically, I'll say, I can maybe give you a picture. If you have a solenoid with a B field, and you consider, like, this is very, very heuristic, but if you consider like a wave packet that travels around, when you do that, you get, if you just travel around it, of course, you know, because it happened over some time, there's like the dynamical phase, it's like e to the minus et over h bar that it'll pick up. But even if you account for that, there's actually like a non-trivial phase that it picks up every time you go around it, even though it should literally be like the same. And the way that you measure that is by, like I said, with interference, you send sort of two wave packets around, then you let them interfere and you get this like double slit pattern, and what'll happen is the B field will actually shift the pattern somehow. So this is a really weird thing, but it is probably like the poster child of the non-trivial effect of quantum mechanics coupled to electromagnetism. Now this one is cool. I won't say more on it right now because we'll get into the weeds of it. The second one is arguably it should be worse because it's really weird, but it's, or because initially it seems weird, but it's, I think, actually a little easier to discuss right now. And that is once we talk about the Ahern-Bohm effect, we're going to discuss magnetic monopoles. I know, so I'm going to assume all of you have all of you taken 24 at least, or like an equivalent? Is that? Okay. You've taken 110B.
I don't know.
Okay. So all of you should be probably familiar with the idea that like this shouldn't exist. Right? This is like a thing that you learn. Is like this doesn't really exist, and yeah. I mean, we haven't observed one, right? We'll explain why this is important shortly, but yeah, magnetic monopoles are weird. Let me say Dirac magnetic monopoles. You can come up with a way to make like a non-trivial magnetic monopole by doing this. So if you have a solenoid, say, this is described in this paper, it's like Dirac 1931, or I really like Leonard Susskind's book on special relativity that talks about this, like the pop science one. So if you imagine like a magnetic, a solenoid, so it's got a B field is going like this, and then you imagine like, well, this is going to basically look like a magnetic dipole. So you sort of go, you know, the fields are going to look something like this, right? And that's pretty much like, it's like you have a pole here and a pole here. But if you imagine instead sending this guy, right, out to infinity. Okay, so I send that end all the way out to infinity. Well, now you've taken a dipole and you've pushed one of the poles out to infinity. So you have a monopole because the pole is at infinity. So it's going to look basically like this, right? So this is kind of like a monopole field. So it's like you can kind of construct something that kind of looks like a magnetic monopole. Of course, it's not, because you have a solenoid, and you can see the solenoid probably. But as far as quantum mechanics is concerned, you basically have only a few ways. Like if you assume that this is, say, infinitesimally thin, for example, so you could never like scatter off of it or something, or you could, but like you can't like do a classical experiment. But like scatters off of it, maybe there's some interference or something. What is shown in Dirac's, what am I thinking? Paper is that the non-trivial effect of quantum mechanics coupled to electromagnetism is that if you have a magnetic charge, G, is that you actually require a quantization of the magnetic charge via the electron's charge. And so this is a very classic result. So we'll discuss this as like an important quantum theory of, or important quantum mechanical, and sorry, I'm being a bit rambly now. This is an important consequence of coupling quantum mechanics and particularly the phase, and in fact also the Ahern-Bohm effect, to classical electromagnetism. So that's like sort of the first part of the second part of this course. This was the section when I was writing this, I was like a little worried that I might lose people. It seems a little bit esoteric. Why do we care about it? And we will expand upon that now. Okay, so now we're going to move into, and we'll, even up to this point, we're still sticking with this hydrodynamic formalism of quantum mechanics. We're working in a regime where it's like, it's mostly, you can understand it like this, and it's really physically intuitive, that's why we're doing it, but it's not, at this point, once we built up enough of a physical intuition, I'm going to move to a more general framework. So we're going to move to a framework where, let's say I'll generalize, which is more in line with sort of like the standard literature on this stuff. I'll say, also, this is about the cutoff sort of halfway through this, and about this is the cutoff where we move from that book, The Quantum Theory of Motion, to the David Tong notes. So like now it's going to be much more referencing that, generalize. And we will sort of re-derive most of the things, talking about electromagnetism and the Aharon-Bohm effect, from a more standard framework, which all starts with the idea of an adiabatic process. So let me say, do people have an idea of what an adiabatic thing is? Yeah.
Well, change in entropy 0.
Right, so that's the thermo, also static, but we'll say thermo.
It's certainly one of those definitions.
Yeah, so delta S equals 0 is like an adiabatic process, right? Or equivalently, or maybe not equivalent, you might have also like learned like no heat transfer, which is, it's the same thing, right? Because it's like ds equals dq over t, I think. Yeah. So it's like this is the one that you're familiar with. It's like it's a process that happens and there's no change in entropy, or there's no heat that's added or leaves a system in thermal. And that makes sense for thermal. That is how you define it. It's like a perfectly good definition. But in quantum, we have to clarify it a bit more, because in quantum, all of this is to do with entropy or energy, and energy is like not so nice. It's not this continuous thing that you can just think about. It's now possibly quantized. So we're going to talk about how in quantum mechanics, the way that we sort of work with a system that is adiabatic, you could even work with a system that's like a one-particle adiabatic system, which is to say that if you have, which is like an analog of this no heat transfer thing or this no change in energy thing. And that is going to be, if you have a Hamiltonian, which has some amount of energy, right? Or so, I mean, it has some set of energy states. Let's say that, and this is over time, because we're talking about a process that occurs over time. Let's say that this is at t equals 0. And say that at time t equals 0, you have some discrete energy levels of your system. If you then, let's say, okay, we have if you sort of then consider the Hamiltonian evolving over time, you can imagine that these energy levels are going to sort of generically change however they might change. Importantly, there's one property of them which we will assume. So you can see we're just tracing these. I guess also really what I'm saying is this is like the ground state, the excited state, second, third. We're sort of tracing the energies of the various eigenstates into those tests. We're going to assume that like there isn't a level crossing, so we're going to assume that you don't have something like this. Okay. There's reasons why that like very rarely happens. In fact, you have to have normally you have to have a symmetry that protects that. So we'll assume that that's not the case. And furthermore, you can imagine in that scenario, you also have you have an energy degeneracy of the two levels right at that crossing point. So we're going to assume there's no energy degeneracy at all. And we'll also assume that these gaps between the energy levels are finite, because that's really when it's the quantum mechanics that we care about. So no degeneracy.
Well, I need to go to a section because I have to change the second time. Like, can you just mark me as present?
Did you sign in?
Oh, wait, where's the sign sheet?
You should just sign in.
Oh, okay.
I'll
do that for you.
Yeah, sorry, where was I? So let me write that down. So no degeneracy, and no, I guess that also implies no level crossings. Okay. The quantum way that we're going to sort of define or I won't prove, but we'll state this thing called the adiabatic theorem. This is the quantum adiabatic theorem. Basically says that suppose you start in an eigenstate at, I'll use green, at t equals 0. So suppose we start in psi 1. It pretty much says, we'll make this more precise, that if h of t varies slowly enough and start in, let's see, psi 0 equals, say, n of 0, where that's an eigenstate. If h of t varies slowly enough, given these premises, then if we start in an eigenstate, then we will remain in that eigenstate over time. It's not going to sort of move into the other eigenstates. That's what we'll define as an adiabatic process. Yeah.
This is coming with the statement that there's no level crossings.
Yeah. That's what I.
Right.
Yes.
If there were level crossings, which you kind of said that there has to be some sort of weird degeneracy thing. But like, suppose there was a level crossing, kind of like what would happen if you try to vary a system adiabatically?
You can't. I mean, the adiabatic theorem doesn't apply there. Like, there is actually one case that people care about, which I don't. Have you heard of spectral flow? I don't know if that's.
I don't think so.
There is actually a case where we will consider a system that does that, but that's just not applicable here. That's just that we're not actually going to consider. I mean, there are ways to make it.
Well, I'm just like asking, like, what would happen? Like, would there be kind of weighted probabilities of like going into one or the other state, like after the level crossing, or like?
I think but it like probably depends on how you do it.
Yeah.
Like, it's kind of just, this is mostly like, okay. I'll say right now, like, let's say, so the thing, no degeneracy implies no level crossings, right? Because you have a degeneracy at the level crossing. If you have, like, say, two degenerate eigenstates, okay, but like, let's say psi 0 degenerate ground state, you know, if the Hamiltonian is perturbed over time in such a way that those split, say, then that's just not, like, you can't, I mean, this just doesn't, like, really apply. But if like, I think that what you said is correct. That's like, I mean, there would just be there's some room for them to split, you know, some room for the state to like move into the other two. But like, you could generalize this somewhat to degenerate states, assuming that those degenerate states don't split. And then that just means that you kind of have to like track the states in some way that isn't with energy. That is not abelian anyways, so we'll, we will maybe talk about that, but probably not. The degeneracy is a significantly more complicated case. Maybe let me make it slightly more clear by finishing this. If we start in this, like I said, we'll stay in this. So can anybody sort of say what this line should be if I write psi of t?
N of t.
Let me. Right, so n of t, but the state is only determined up to a phase. So it's up to a phase, which I will call u of t. In the case of degeneracy, this could be a unitary, not necessarily a phase. So the thing that we'll care about, maybe, I guess I'll break my like one section per topic rule. The thing that we're going to consider then is, well, what happens if, let's say, how does the Hamiltonian depend on time? We're going to use this and we're going to say, well, H depends on time as, it depends on like degrees of freedom, which, yeah.
Wait, I just want to clarify. You've written this as u of t rather than e to the I alpha of t, because in the case that there is degeneracy, this is a unitary operator, or?
I mean, okay, maybe I can elaborate on that. Yeah, like imagine that you have, maybe this is like psi naught and psi naught prime. This is pretty complicated, but suppose you have two fold states, then, and assume that they don't split. So it's a special case that perturbing the Hamiltonian causes them not to split. That's not generally true, but if that's the case, then all you know is that you're within the state, like if you start in this degenerate subspace, all you know is that you stay within that subspace. You don't necessarily know if you're in one state or the other. So you can kind of, then it's like your basis is twofold. So it'd be like saying, let's see, it's degenerate is like saying, if you start in psi 0 of t, or if you start an n, no, I use psi 0 of t, psi 0 prime of t goes to a unitary acting on, or 0, where this is now u of psi 0 of t, psi 0 prime of t. So like, my point is that now your basis is, your state basis is twofold, and so you have like a unitary operator, which instead of just an overall phase, the phase is a unitary operator for 1x1 matrices. And the reason why this is so interesting in a lot of condensed matter systems is because matrices don't in general commute. So you can have non-trivial things happen. Okay. Continuing, this isn't still within the same lecture. I maybe went into more detail on this than I meant to, but that's fine. We're going to consider, well, how does the Hamiltonian depend on time? It could depend on time in a lot of ways. I mean, you could imagine it, but the way that we'll care about, and this is maybe the experimentalist coming out in me, is suppose that you have a Hamiltonian which is dependent on, let's depend on degrees of freedom, which I will use Q to denote. Q hat mu, so Q hat mu is, Q hat mu is like, this is degrees of freedom, like position, momentum, maybe spin, that type of thing. So it's dependent on those, and those exist. But we'll say that the time dependence, like these aren't, we'll take those to be non-time dependent. We'll say that the time dependence of the Hamiltonian has to do with parameters that we vary. We'll say, okay, suppose we have a system, I'm going to, as an experimentalist, vary a parameter over time, and that's where the time dependence of the Hamiltonian is going to come in. And I'll call those parameters lambda sub I, and I'll say explicitly of time. So this is the type of Hamiltonian that we'll consider. Then the time dependence all comes from these parameters. If you imagine then, like I have, let's say I have a two-dimensional parameter space. Let's say I have one, like each of these is like a knob I can turn, so I can turn one knob going this way and one knob that way. If you have a, let's say lambda 2 of t, lambda 1 of t, and this is now parameterized, if you imagine that you start in some point in parameter space, and then we do an adiabatic evolution of this thing. So let's say I evolve it up to here. Okay, so this is following some path in parameter space, and this is an adiabatic evolution, so I varied it slowly enough such that the only thing that changes is the phase. We will show that this thing has a quantity which depends on, like the phase depends on quantities that are dependent on the parameters as well. And the thing that will matter is kind of like in the Aharonov-Bohm effect that I discussed, or actually exactly like it. If you imagine moving in a closed loop, so I'll say like this, so you start here at time t equals 0, and then you end here at time equals like big T or time equals tau, then the overall phase, u of t, is going to be equal to a term which is like e to the minus I e n t over h bar, where this is like the n denotes the eigenstate that you started in, times this thing called a geometric phase. And this thing is kind of like the thing that affected the phase in the Aharonov-Bohm effect. So it means that you can sort of move along a closed path in parameter space adiabatically, and yet when you return to the final state, you'll have a phase which somehow depends on the path that you took. And this thing is also called a vary phase. Okay, and then like, let's say, this is probably ish where we'll end. I mean, there will be more, not with the class, but of lecture 5. I haven't worked out exactly the delineation for this, but roughly this is where lecture 6 starts, because what we're going to discuss is how this phase that is picked up by the quantum wave function over some varied path and parameter space actually has to do with curvature of the parameter space. So I'll draw the, this is a pretty famous picture. So imagine you have a sphere, and let me imagine that like the sphere is, this is our parameter space. So imagine you have like angles, you have like, if you have a vector on the sphere, you have angles theta and phi. So like your parameters correspond to like theta and phi on the sphere. Sorry, does that make sense? Like your parameter space has the geometry of a sphere. I don't know if that's, do people understand what that is? I don't know if that.
Are you talking about like lambdas?
Yeah, I'm saying like this state space, it's like if you were to travel far enough in this direction, you come back here. If you travel far enough in that direction, you come back. It's not a torus, it's a sphere. But like the idea is that the way that you have to parameterize this is on a sphere. Like it has the, let's say, the topology of the sphere.
You're saying that the above statement about geometric phase only applies if the parameters that you choose have this property, or you're saying that this
I'll do
arises from any such parameter that you can vary in time?
Well, it depends on the geometry and topology of the state space, and this is an explanation. This is going to be an example of how you can intuitively see that.
You're saying that it's a condition on the types of parameters that you can have, not that
It's a condition on when the parameters.
create a geometric
Yes,
phase.
yes,
Okay.
that's what I'm saying. Yeah.
For those of us who don't know too much about topology, do you think you could draw like where the parameter would come back?
I'm gonna draw. This
Oh,
is this
okay,
picture.
okay.
Yeah. So this is if you've ever heard of the Foucault pendulum, this is that. It's not. I won't be the Foucault pendulum. You can imagine. I'm sure you've seen this before, right? So you can imagine, right? If you have the wave function, it has a magnitude. Wait, oh, sorry. I thought I saw a. It has a magnitude, and you can imagine the phase, right? It's like on a circle, right? Because it's e to the I theta. So you can imagine that phase as being like a vector that is emanating from the magnitude. And at every point you assign a vector that's pointing somewhere. And the only thing that matters is the direction. The magnitude is 1. Okay? So let's imagine that you start at like the north pole of this thing. And we have, let's say the phase is pointing out like this. There's some sense in which it's a little confusing because it's like, well, it's pointing out of the sphere now. We care about the direction. So it's like, you could imagine sort of shortening it, for example. It's like there's a direction that it's traveling. Let me maybe travel it like this. So it's pointing like this, and the idea is that this phase is tangent to the sphere. Why is that? I don't know, we'll get into it. But imagine that like the phase is a vector which is always tangent to this sphere in parameter space. Okay, sorry, this is maybe a harder thing to grasp than I initially thought. But that's what this is representing. The arrow is representing the phase of the wave function. So now if I travel along a path in parameter space, okay, and you want this to stay tangent to the surface in parameter space, you can imagine traveling along, say this is along like a great circle, so we travel like this. And if you keep the phase, assume it's adiabatic transport sort of parallel to the surface, then at the bottom of this path, it's going to be pointing down. Does that make sense to people? I don't know if that's, do we see why it would be pointing down if you sort of imagine this should be like pointing horizontally, like this is pointing.
But a phase lives on a circle when you're moving on a sphere, doesn't it? I mean,
Yeah. Well, yeah. So this is a bit. This was where I realized it's a little bit hard to do this whole synthesis of the class, but like, what you're imagining is like imagine you have like a plane that's tangent to the sphere. So imagine that this plane is tangent. This is hard to draw. Okay, and what we're doing is as we move it, the plane is tangent to the sphere, and there's a circle in that plane, and you're sort of moving the plane such that it's parallel or tangent to the sphere, and as you do that, it kind of, in the plane, the vector is pointing the same direction. Maybe I drew it poorly. So this should be like, yeah, it should be something like this. In the plane, the vector is always pointing, say, down in the plane, but if you look at it like from the outside embedding, then you can see that it's sort of moved relative to the sphere, but relative to the plane, it sort of remained the same. I don't know.
So are you saying that we've represented the complex plane as the tangent space of some sphere?
Yeah, that's what I'm saying. Yeah, yeah, yeah. It's like a. This is a hard thing to talk about without being formal about it, but yes, pretty much.
I guess like another question I have is like just to kind of reiterate earlier, like, okay, what if I chose experimentalist? Okay, one dial I can have is like temperature, right? I can vary temperature and time however I want.
Yeah.
Right? Is temperature a valid parameter that satisfies this like condition?
Temperature, I think.
The geometric phase, or like what parameters could one vary? Where
Magnetic field is the big one.
I see.
Let me maybe say more about that in a second. But magnetic field is the one that we're going to care about most here. Although we won't actually be varying. It's a little bit different. You don't like whether or not. Let me finish this. So let me just finish this and then you can say more. And then let's say I move it such that it's like in the XY plane, I move it by an angle of phi equals 90 degrees. Okay, and then when I do that, you can sort of imagine I still have like a plane that's like this, and then I have a vector that's pointing down, right? But then then I move it all the way up along some, like, again, an adiabatic trajectory, what you'll find is that now the vector is pointing like that. Okay, so this is like, the idea is that what you've done is an adiabatic transport process on a curved parameter space, and overall you had a change in the angle of it, even though you sort of moved it in this adiabatic way. Maybe this wasn't the best thing to discuss, but I don't know, this is the thing that, to me, makes it the most intuitive why this is. And again, all of this matters going back to what we discussed in the beginning of like phase being important and phase having effects on like the velocity field of the fluid. That's the original intuition we had. Okay. Luckily, we're mostly done with this discussion now. This is like the second part of the course. Does anybody have more questions on this? I'm very happy to answer. I just want to make sure.
Right.
Yeah, so it's.
Well, but EVI, ENTH, I mean, EN depends on time, right?
Right.
So you probably want it as an integral. I mean, the energy levels you're drawing there is very.
Right, but sorry, I guess I should say that I'm assuming that once you return to this, like you're at the same parameters, so this is the same energy level. Like I'm saying, let's say.
Oh.
I'm saying like you go from here and let's say that this is at some energy level and like here at time t, you return to the same energy level, right? That's kind of the idea of like, you know, if your parameters are the same, you should have like the same eigenstate if you did an adiabatic transport up to a phase, right? I think that's correct. Not counting, you know, the degeneracy and stuff. Yeah, I think you can say that. Yeah, I think you can say that. Yeah. Okay, are we good on this? I know this is the most confusing part of this, so yeah.
So in your explanation using this sphere,
yeah,
are you kind of saying that the geometric phase in this case kind of corresponds to an extra 90-degree rotation?
Yeah, in this case, if you do this specific path, or you can imagine if I'm only moved like to here and then moved up, it wouldn't be 90, right?
Yeah.
So, okay, the punchline of this is that this curvature, this is a property of the fact that your parameter space is curved and has a non-trivial actual topology, but also a non-trivial curvature. And what you actually can, maybe we will talk about this curvature corresponds to the curvature that you would get for a magnetic monopole.
Oh, you're saying specifically a magnetic field has a curvature that looks like that. Like, and other parameters can have some different curvature, and there's like, it can be more complicated, but it's like a sphere for.
Yeah, well, not necessarily magnetic field specifically, but like magnetic monopole, yes. It's hard to make this statement precise right now, but pretty much, yeah. It's not always like this. Sorry, let's say this is an example.
I see.
It's not always like this. If your parameter space is flat, then imagine okay, the word is parallel transport. Imagine transporting your vector along this flat thing. It's clearly not going to change angle, right? So my point is, as opposed to this, where let's see, maybe I should have drawn it. If I have a vector and I transport it such that it's always parallel to the plane, it doesn't change any angle. The point is that, as opposed to this, if you have a curvature, then this angle change is non-trivial. And that's going to be a geometric way to think about what's happening in all of this. And yeah, so the punchline here will be relating back to 4, is that this somehow corresponds to the magnetic monopole. But the point is that now we don't just have like a, this is hard, like probably don't try to understand this yet, but this correspondence now is not just in, like, magnetic field is like a thing that exists in position space. Right? It's like we know that this exists, and if we chose position space, say, to be our parameter space, say this was x1 and x2, then you couldn't do this, assuming you don't have, because we don't have magnetic monopoles. But in parameter space, you can have things that act like magnetic monopoles. Okay, that's the punchline. So that's why the magnetic monopole argument mattered before, because you can have things that act exactly like or pretty much like magnetic monopoles in parameter space. And that parameter space can then that can create non-trivial effects. The other big thing that we'll talk about is that in this topic is that sometimes, maybe I won't mention that yet, but sometimes if you consider integrating the curvature of this thing through some area, this curvature, for example, in magnetic, if this was a magnetic field, if it corresponded to a magnetic field, right? This is Gauss's law for a magnetic field, so this should be 0. But if this is non-zero, then that's when you have like a non-trivial effect. And that's when all of this discussion matters. It's when you can have this like kind of point sources. Okay. I think that's all that I should say about this. I don't want to. Yeah, this is definitely going to be the conceptually or the mathematically hardest part, but I will try to not make it like I won't be doing. If there is differential geometry you need, I will make it clear. I won't like assume you know anything about that more than like simple vector calc. Okay, so that's actually like the bulk of the general things in this course. We built up. I erased the previous parts, but we built up quantum mechanics. We built up the role of phase in quantum mechanics. From that, we got electromagnetism. We then discussed the quantum implications of electromagnetism, these weird things like the Hubble effect and magnetic monopoles. We generalized our theory to now encompass, right, we'll be able to understand this in the magnetic monopole in this framework. And now we're finally ready to talk about what is pretty much the ultimate thesis of this course, which is this is going to be lectures 7 and 8. This is the quantum Hall effect. Okay, so this is like the last part of this course. And I don't know if anybody's going to have this objection, but I'm going to say integer here. If you don't know what that means, but that's really what I'm talking about. So this is like a culmination, and unfortunately right now I probably can't say exactly why this is so relevant to that, why that is so relevant to this, but to me, this is like one of the coolest things ever. It's let's say, a macroscopic consequence of quantum mechanics that you see in experiment and has like a really, really remarkable result. I think that like some, it's not the only macroscopic result in quantum mechanics. You have like black body radiation is one. The other cool one in condensed matter is superconductors, right? So it's like a very non-trivial thing. This one is probably a little less known, but I'll quickly go through a brief overview of what it is, and when we actually explain all of this, then we can tie all of it back to this. So briefly, the Hall effect is a pretty, the classical Hall effect is, imagine you have, okay, we're gonna just assume like it's a strip of wire, and you have some current running through it, I, or J or K or whatever is the density. This means that you sort of applied an electric field like this, right? So you just applied an electric field and you have it, well, maybe you should, imagine you have leads here, say. And that's, I mean, that's like 23, 24, that type of thing. It's a very simple thing. You can use Ohm's law, for example. But the Hall effect says, okay, now let me apply, I used orange, right? Yeah. Apply an out-of-plane electric field, or magnetic field, to this, so it's not just there, it's everywhere. A uniform, say, magnetic field to this strip of conducting wire. If you do that, then let's assume the electrons have positive charge so we don't have to be confused. Using the right-hand rule, what is it? It's like, so the current is going that way, the field is going that way, so I think the force on the charges would be down. So you can sort of think that like what's going to happen is the charges are going to get deflected down. And so what that means is that you'll have overall like a voltage drop across like the sides of the wire. And this is what we call a Hall voltage, because it's sort of, you apply an electric field this way and you get a displacement, you get a voltage in the orthogonal direction. So Hall basically just means orthogonal to the field. You also can get like a Hall current even, and if you have a Hall current, that implies that you have a Hall resistance. So you actually have a resistance which is orthogonal to the direction that you apply an the electric field. So it's just like classically you can think about it's because you deflect them, so you have builds up of charge here, and so there's a voltage drop. Right? So if you do the math, it's a very simple thing using like Drude model. You don't know what that is, but it's a pretty simple physical model to say if you plot like the we'll do versus magnetic field versus, so we have like the applied magnetic field. You can imagine if you increase the magnetic field, you should expect that more charges get deflected, or overall more charge is deflected to this side, and so you would get a bigger voltage, and so and you get like maybe a bigger, smaller current, bigger resistance, I think. Yeah. So like as you increase the magnetic field, you get a bigger resistance. So this is this, and this is our Hall. And you can just work it out that like in a sort of classical like ohmic theory, you should just get that the field, let's say, that the relationship between the magnetic field and the resistance is entirely linear. Okay, so as you increase field, you just get a great increased resistance. If, however, in certain materials, actually in a lot of materials at low temperatures, you get a very, very, very different dependence. And that dependence looks something like this. It kind of looks something linear, and then at a certain point, I guess this is the Hall one, you start to get steps like this. And then it sort of plateaus off at a certain point. And these lines are like really straight. These are straight. I guess let's say horizontal. They're pretty much completely horizontal. Like it's like this is, I think there's a video I saw, like this is maybe the straightest line that anybody's ever measured. I'm not sure if that's a true statement, but like it's really straight. Like it's like really, really straight to the point that this is used to, I don't know, this is, what do they do this in metrology for?
For the unit of resistance.
Yeah, okay.
Defining the ohm.
Right, yeah, to define, because this is so accurate, you can use that to define the ohm. And let's say, the reason why you can use it to define the ohm is I am embarrassed now, because I forgot what the relationship is based on fundamental constants. Hall resistance quantization. It is, yes.
What do you want, the H over E squared?
Yeah, but there was I wanted to make sure I didn't say that wrong. So like the thing is that like this quantization isn't dependent on material really, almost. and even if it is dependent on material, it's only like up to like a constant simple factor. It's pretty much universal in the materials that do exhibit this, that the resistance, Hall resistance, maybe should it be the resistivity? Right, it should be the resistivity.
In 2D, it doesn't matter.
Right, I guess it doesn't matter, yeah. The Hall resistance is quantized by just fundamental constants, and those fundamental constants are h over e squared.
It's H over E squared.
Yeah, sorry, I don't know why I'm forgetting this right now. Quantized by h over e squared, and then there's an overall factor here, which is a thing that we'll sort of describe as being sort of a filling number, but we'll call it mu. And it's quantized, like in each of these steps, it's quantized.
H over nu E squared.
Yes, sorry, it's quantized by h over nu e squared. Okay, sorry, that's, yeah. Quantized by h over nu e squared. And this is like, so you can see this is dependent on just h, just e, and just like an integer. So that's why you can use it to do metrology on like resistance, because it doesn't depend on the material. On the material. So that was nice chalk too, but, and we'll sort of talk about how all of this is related to that, and that will be sort of the final big topic of this course. We're probably going to spend, it's 2 lectures because we'll probably do one introducing it and one discussing how all of this is related. And you'll notice I said 9 lectures, so there's one more that's available for like whatever you want to do. Like we can do, I have ideas, we'll see how it is, but I wanted to make it, so this sort of the 8 lectures are the main bulk of this course. I think that's all I wanted to say for today. So let me then I'm doing the sort of open discussion section.